I will continue chapter 5 from here. Let me add chapter 5 PowerPoint screen. So on the previous lecture, we covered section 1, 2, 3, and 4. So on this section, we are going to continue with 5, 6, and 7, and 8. So in section 5.5, we are going to learn about the zeros of a polynomial. So we learned about some theorems that can be used to identify the zeros of a polynomial. We will evaluate polynomials using the remainder theorem, using the factor theorem, using the rational zero theorem. We find zero of polynomial functions, use linear factorization theorem to find polynomial with given zero, and using the Descartes rule of signs, and solve some real world application of polynomials equation. So the remainder theorem says that if we can divide a polynomial by the expression x minus k, then the remainder is the value of f of k. So use the remainder theorem to evaluate the polynomial function f of x equal to x4 minus x3 minus 15x squared plus 2x minus 2 minus 7 at x equals to 2. And so we can solve this equation using the division rule, the synthetic division. So we consider that our factor is x minus 2, so we will write 2 here, and we will bring down 6, multiply 2 by 6 to get 12, adding to negative 1 to have 11, multiply it by 2 again to get 22 that we write here, add to minus 15 to have 7, multiply 7 by 2 and write it here, add to 2 to get 16, and multiply 16 by 2 to get 32, and subtract 7 to have 25. So it tells us that 25 is the remainder in the division of f of x by x minus 2. So f of 2 equals to 25. So this is an easy method of finding the value of a function at a point, dividing it by the factor x minus k. Another theorem is the factor theorem. According to the factor theorem, k is a zero of f of x if and only if x minus k is a factor of f of x. That is, when you divide f of x by x minus k, you have a remainder of 0. So the synthetic division is used to divide the polynomial by x minus k and confirm that the remainder is 0. That tells us that x minus k is actually the factor. We can use it also for quadratic expressions or cubic expressions. If possible, we can factor the quadratic expression using the method that we already learned for how to factorize a quadratic function. So we show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. So we will divide the cubic polynomial by x plus 2. Using synthetic division, k will be minus 2 here for x plus 2. That is x minus minus 2. So we bring down the leading coefficient of the leading term 1, multiply it by minus 2, and to get minus 2, add minus 6 to get minus 8. Minus 8 times 2 is, minus 8 times minus 2 is 16. Add minus 1 to get 15. Multiply 15 by minus 2 to get minus 30. And we get a remainder of 0. So x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. So the remainder is x plus 2. The remainder of the division of the cubic function by x plus 2 is 0. So it is a factor of the cubic polynomial function. So we will write it and use the division that we just made as we use the division here, we will know that from a cubic function divided by x plus k, it will give us x squared minus 8x plus 15. So that is the other factor of the division by x plus 2. So now we can also use the factorization theorems for quadratic functions to factor x squared minus 8x plus 15. We can factor it, taking factors of 15 that add up to minus 8r, minus 3, and minus 5. And so we can find the complete factorization and determine the zero of the polynomials are as minus 2, 3, and 5. So we can also use the rational zero theorem. If we have a polynomial function, an xn plus an minus 1 xn minus 1 plus a1x plus a0, the rational zero theorem states that this polynomial function has integer coefficients, then every rational zero of f of x has the form p of k. That is assuming that an minus 1, and a1, a0, the coefficients are all rational numbers or integers. They are all integers. If they are rational number, we can make them into integers anyway by multiplying by the common multiples of all the denominators. So if they are all integers, then every rational zero of f of x has the form p over q, where p is a factor of the constant term a0, and q is a factor of the leading coefficient an. So when the leading coefficient is 1, the possible rational zeros are the factors of the constant term a0. Let's look at an example. So in general, how do we use the rational zero theorem? First, determine all the factors of the constant term and all the factors of the leading term. So determine all possible rational values, p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. Be sure to include both positive and negative candidates. Then determine which possible zeros are actually zeros by evaluating f of p over q. So consider the polynomial function f of x equal to 2x4 minus 5x cubed plus x squared minus 4. So the constant term is minus 4, and the possible values of p are plus or minus 1, plus or minus 2, and plus or minus 4. The leading coefficient is 2, so the possible factors of 2 are plus or minus 1, plus or minus 2. So possible values of p over q that are candidate to be factors of the zeros of the polynomial are p over q. So we can now use each of those factors and check if they are actually zeros of the polynomials. So the possible values are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus half. So which we can fit into the function, and whenever we get 0, we know that we have a 0 for that polynomial. Section 5.6, irrational functions. In this section, we will use the arrow notation, which is used to express limits. We will learn how to solve applied problem involving rational functions, how to find the domain of a rational function, identify vertical and horizontal asymptote, and graph rational functions. So the arrow functions is generally used to express what in mathematics is called the limit of a function. So when we write x arrow a superscript minus, it means x approaches a from the left. X approaches a from the right is x arrow a plus. x goes to infinity, x goes to minus infinity, f of x approaches infinity, f of x approaches minus infinity, f of x approaches a. That's the meaning of the arrows that we may be using when we are writing mathematically. Let's consider the function f of x equals to 1 over x. The graph of the function is given below, and we can see that as x tends to negative infinity, f of x tends to 0. As x tends to 0 to the left, f of x tends to negative infinity. 0 to the left is the negative part. It approaches 0 from the negative part. As x tends to infinity, f of x tends to 0. And as x tends to 0 positive from the positive part, f of x tends to positive infinity. So a vertical asymptote of a graph is a vertical line x equals to a, where the graph tends towards positive or negative infinity as the x values tend to a. So for example, here, as x tends to 0 positive, f of x tends to infinity. So x equals to 0 is an asymptote. So there's an asymptote, a vertical asymptote for this function. A horizontal asymptote is a horizontal line y equals to b, where the graph approaches the line as the x values approaches infinity. So we write that as x tends to infinity, f of x tends to b. Then y equals to b is a horizontal asymptote. For example, we know that as x tends to plus or minus infinity, f of x tends to 0. So y equals to 0 is called a horizontal asymptote. So we can see the line here. The line y equals to 0 is the x-axis, is a horizontal asymptote, the green line. Domain of a rational function. The domain of a rational function includes all values, all real numbers except those that cause the denominator to be 0. So when we are given a rational function, to find the domain, we set the denominator to be 0 and exclude all the values that makes the denominator 0 from the set of real numbers. Example, if we have a function x plus 3 over x squared minus 3, then we can see that x squared minus 3 is 0 at x equals to plus or minus 3. So the values plus and minus 3 are not part of the domain of this function. So to identify the vertical asymptote of a rational function, first step, factor the numerator and denominator. You may observe that numerator and denominator may have a common factor, so you simplify it. Now consider those values that will make the denominator 0 while the numerator is not 0. And those are the values for which we will have a vertical asymptote. Example, identify vertical asymptote for the following function. The function is k of x equal to x plus 2x squared over 2 minus x squared. We can factor the denominator. We cannot factor the numerator because it's the sum of two positive numbers. And then we will observe that the denominator can be 0 at -2 and 1. So those two values are the vertical asymptote because as they go to 0, the numerator will not be 0. So the function will go to infinity. So this is the graph obtained from a graphing device. And we can see two vertical asymptotes here at -2 and at 1. There is a horizontal asymptote here at x equals to -2 as well. So if you look at the function, you will see that as x tends to infinity, we are going to learn this later, as x tends to infinity, f of x will tend to -2. That's what gives the horizontal asymptote that we have here. Removable discontinuities as those functions that will make both numerator and denominator 0 and could be simplified to actually obtain a value which is not infinity. Example, if we have a function f k of x equal to x minus 2 over x squared minus 4, then we will see that both numerator and denominator are 0 at x equals to 2. If we can simplify this function, these factors, to both numerator and denominator, we will have k of x equals to 1 over x plus 2. We will observe that both 2 and -2 were not elements of the domain, but at 2, we have a limit which is not 0. I'm sorry, which is not infinity. The limit actually exists. And we will see that k of 2 will be 1 over 4. So the limit of f of x as x tends to 2 will be 1 over 4. So 2 is a removable discontinuity. So this is the value of 2. We have a circle at the point 2, which with the image, if you look very well, when I will increase the graph, you will see that normally at 2 here, we are supposed to have 1 over 4. But because the function was not defined at 2, it is a removable discontinuity. The function would have otherwise been defined if it was not 0 at the denominator. So if 2 was not removed at the denominator. So that's what we call a removable discontinuity. For horizontal asymptote, we take the limit of the function as x tends to infinity. If that limit is not exist, if it is not infinity, we will have a horizontal asymptote at the point where the denominator at the point where the limit at the value of x is not 0, the limit at infinity. So let's consider these two functions. The first one is g of x equal to 6x cubed minus 10x over 2x cubed plus 5x squared. To determine if the limit at infinity is not 0, look at the highest degree of the numerator and the denominator. If both numerator and denominator are polynomial of the same degree, just take the fractions of the leading terms of those two polynomials. For g of x, the leading terms are 6x cubed and 2x cubed. If we take those fractions, we will have 6x cubed over 2x cubed, which is 6 over 2, equals to 3. So the line y equals to 3 is a horizontal asymptote. Now let's look at the second function, h of x equals to x squared minus 4x plus 1 over x plus 2. Here, numerator and denominator have different degree, and the degree of the numerator is higher than the degree of the denominator. In this case, a synthetic division could help us to see a type of asymptote which is called a slant asymptote. Actually, it is the equation of the remainder in the division by x plus 2. So now we have divide this function x squared minus 4x plus 1 by x plus 2 using synthetic division. We will have here normally we should have here -2. So this is a mistake. It's -2 when you are dividing by x plus 2. Negative 2 times 1 equals to negative 2. So we add to negative 4, we have negative 6. Then negative 2 times 6 is 12. Add to 1 is 13. So when you are dividing x plus k, always use k. So it's minus k, I'm sorry. So in x plus 2 here, you should have minus 2 here. The minus was omitted. So the quotient here is x minus 2, and the remainder is 13. So this is x squared minus 4x plus x plus 2 is equal to x minus 6 plus 13 over x plus 2. That's actually what this expression means. Here we have x minus 6 with remainder 13, which is 13 over x plus 2. So the line so the quotient is x minus 2 and the remainder is 13. There is a slant asymptote at y equals to x minus 2. Intercept of rational functions. A rational function will have a y-intercept when the input is 0 if the function is defined at 0. So the y-intercept can be obtained when we can find f of 0. Otherwise, there is no y-intercept. The rational function will not have y-intercept if the function is not defined at 0. So remember that the y-intercept is the value of y when x equals to 0. So if 0 is not in the domain, there will be no y-intercept. Likewise, a rational function will have x-intercept if the input that caused the output to be 0. That is, if 0 is in the range of the function. If 0 is not in the range of the function, there will be no x-intercept, meaning that the function is not going to pass through the x-axis. Consider the function f of x equal to x minus 2 times x plus 3 over x minus 1 times x plus 2 times x minus 5. So the domain of this function is all real numbers except 1, negative 2, and 5. So we can find f of 0, which is negative 0.6. So y equals to negative 0.6 is the y-intercept. To find the x-intercept, we will solve the equation f of x equals to 0 and only consider the numerator because the denominator is different from 0, then the numerator must be 0. And the x-intercept at the point where x minus 2 equals to 0 or x plus 3 equals to 0, which are 2, 0 and minus 3, 0. So this is the graph of that function. And we can see the intercepts here, minus 3, 0. The second x-intercept here, 2, 0. The y-intercept is at negative 0.6 here. And we have the asymptote, which we could obtain by taking the limit. The limit as x tends to infinity will give us y equals to 0. The limit from the negative side of negative 2 will give us infinity, positive infinity, negative infinity when the limit as x tends to negative 2 from the positive side. So these are the asymptotes. We have 3 asymptotes, vertical asymptote here at x equals to negative 2, 1, and 5. Remember, those are the points that are not in the domain. We get asymptotes there. 5.7, inverse and radical functions. We learn how to find the inverse of an invertible polynomial and how to restrict the domain of the polynomial in order to define the inverse function. So to verify whether or not two functions are inverse, we take the composition of both functions. G composition f of x equals to f composition g of x equals to x. When we have that condition met, we will say that f and g are inverse of each other. Our example here, check if the function f of x equals to 1 over x plus 1 and f inverse of x equals to 1 over x minus 1 are inverse of each other. Realize here that the domain of f is all real except at -1, and the domain of the inverse is all real except at 0. All real except at -1 for f, all real except at 0 for f inverse. So f inverse of f of x will be f inverse of 1 over x plus 1. Replace it in the function f inverse, and we will get x. And now we do the other side, f of f inverse of x, replace f inverse of s in the expression of f of x, and then we will get x. So both functions are inverse of each other. And for that reason, they are both one-to-one functions. So given a polynomial function, to find the inverse of the function, we will restrict the domain such as to have a one-to-one function. Then we will replace y by x in the expression of the equation of the function and solve for y to define f inverse of x. Example, find the inverse of the function f of x equal to 5x cubed plus 1. We start by setting y equal to 5x cubed plus 1 here. Then in this equation, we will interchange x and y. So that's why we have now x equals to 5y cubed plus 1, and then solve for y. So to solve for y, we have x minus 1 equals to 5y cubed. So x minus 1 over 5 equals to y cubed. So y cubed is equal to, we'll say that so, y cubed we will now say that y equals to the cube root of x minus 1 over 5. And we will define f inverse of x to be cube root of x minus 1 over 5. So if a function is not one-to-one, it cannot have an inverse. A function is inversible only if it is one-to-one. So to define the inverse of a function which is not one-to-one, we will want to restrict the domain so as to make it a one-to-one function. For example, if we want to find the inverse of the function f of x equal to x minus 4 cubed, x minus 4 cubed is a parabola which is one-to-one on each side of the vertex at x equals to 4. So either we take the side where x is greater than or equals to 4, or we will take the side where x is less than or equals to 4. So we will solve the equation y equal to x minus 4 squared. First we interchange x and y to get x equals to y minus 4 squared, and plus or minus square root of x equals to y minus 4. We will remember here that in order for this to work, we will either want the square root of x to be y minus 4, or the square root of x to be minus y plus 4. So in each case, we will have y equals to plus or minus square root of x. Because of this type of situation, we will require either that y should be greater than 4 or y should be less than 4 to make the square root of x to be positive. So that requirement is expressed in here, f of x is greater than or equals to 4, or x is greater than or equals to 4. This x, remember that this x here, our x is actually the original f of x, because we have interchanged x by y. So we want f of x to be positive. That is what is the actual meaning of this x here, which for the inverse function is becoming the independent variable. So the independent variable of the inverse function is the dependent variable of the regular function. So that is why you are seeing 2 times x greater than or equal to 4, f of x greater than or equal to 4. And in each case, we have a different function. Though the expression of a function here, f inverse of x equal to 4 plus square root of x with x greater than or equal to 4. This comes from here. If y, when we express here that square root of x equals to y minus 4, we want this comes from the fact that we define the domain of the function where it is 1 to 1. X was supposed to be greater than or equals to 4. So that is why we have here f inverse of x is equal to 4 plus f of x, 4 plus square root of x. And f inverse of x here equal to 4 minus square root of x. So these are the graph of both functions. The first function, when x is greater than or equal to 4, this is the portion of the parabola where the function is 1 to 1. F and F inverse have graphs that are symmetric with respect to the line y equals to x. So we will just fold the graph here to get this value comes here, and symmetric to y equal to x, we will get the graph of f inverse of x for the function x for the domain when x is greater than or equals to 4. For the domain where x is less than or equal to 4, we will take the other side of the parabola, this side, and we will get the graph of the red portion by taking a symmetric graph with respect to the line y equals to x. So depending on the domain you are choosing for the definition of your function in order to get the inverse function, you will have different definition for the inverse function. Let's do another example here. We want to solve an application of radical functions. A mound of gravel is in the shape of a cone with the height equal to twice the radius. The volume of the cone in terms of the radius is given by v equals to 2/3 pi r cubed. Find the inverse of the function v. So v equals to 2/3 pi r cubed, we will solve for r. That determines the volume v of a cone and is a function of the radius r. We will use the inverse function to calculate the radius of such a amount of gravel measuring 100 cubic feet. Use pi equals to 3.14. So we have v equal to 2/3 pi r cubed. Now we will find the inverse of this function as a function of v. So first we set the equation r cubed equals to 3v over 2 pi. So r equals to the cube root of 3v over 2 pi. So when v equals to 100, we fit into this equation to get, let's change this. Also. So the cube root of 300 over 2 times 3.14 is the cube root of 47.7707, which is 3.63. Therefore, the radius is about 3.63. Last section, 5.8, modeling using variation. We are going to look at different types of variation. The first one is the direct variation. When we say that x and y are related by an equation of the form y equals to kxn, then we say that the relationship is a direct variation and y varies directly with or proportional to the nth power of x. The direct variation relationship, where in a direct variation relationship, there is a non-zero constant ratio k. That's the constant of proportionality. So we will say that k equal to y over x raised to power n, where k is called the constant of variation or the constant of proportionality, which help defines the relationship between the variable. So in general, you will be given a problem like if y varies directly with the nth power of x, then you will understand that it means there is a constant k such that y equals to k x raised to power n. So to solve a direct variation problem, first identify the input x and the output y. Determine the constant of variation using the equation k equals to y over xn. Then use the constant of variation to write the equation for the relationship. Now substitute the known value into the equation to find the unknown. Example, the quantity y varies directly with the cube of x. If y equals to 25 when x equals to 2, find y when x is 6. And so to solve this, we will first want to find the value of k. We know the relation is that y equals to kx cubed because y varies directly with the cube of x. So the constant can be found by substituting the values of y and x, which are 25 and 2, and we find k equals to 25 over 8. So we fit it into the equation to have y equals to 25 over 8 x cubed. So when x equals to 6, we have y equals to 25 over 8, 6 cubed, which is 675. Inverse variation is expressed as y equals to k raised to power x over n. That's the inverse variation, where k is a non-zero constant. We say that y varies inversely with the nth power of x if we can write k equal to xn times y. Like in the previous case of direct variation, we want to identify the input x and y, then determine the constant of variation, and use that constant to rewrite the equation of the relationship and substitute the values that we have to get the unknown value. Example, a quantity y varies inversely with the cube of x. If y equals to 25 when x equals to 2, find the y value when x is 6. So now it's an inverse variation, so we will write y equals to k over x cubed as our equation. And we will replace x by 2 and y by 25 to get k equal to x cubed, y. Here we have y cubed. So is 2 cubed times 25, which is 8 times 25 equals to 200. Now we use the constant to write k equals to 200 to write the equation as k equals to k over x4, k equals to 200, so y equals to 200 over x cubed. We substitute x by 6 to have y equals to 200 over 6 cubed, which is 25 over 27. Another type of variation is the joint variation. So for instance, if x varies directly with both y and z, that will mean that x equals to k times y times z. So if x varies directly with y and inversely with z, we will write x equals to ky over z. Notice that we only use one constant in the joint variation. A quantity x varies directly with respect to the square of y and inversely with the cube root of z, the cube root of z. So if x equals to 6 when y equals to 2 and z equals to 8, find x when y equals to 1 and z equals to 27. Solution. Begin by writing an equation to show the relationship between the variables. So we say that x varies directly with the square of y and inversely with the cube root of z. So we write ky cubed over z raised to power 1 over 3. So we substitute x equal to 6, y equals to 2, and z equals to 8 to find the value of the constant k. So we will realize that 6 is equal to 4k over 2 equals to 2k, so k equals to 3. Now we can go back to the equation. Now x equals to 3y squared over cube root of z. Replace y by 1, z by 27 to have the value for x, which is 3 over 3 equals to 1. So this completes chapter 5, and work on your homework. If you have any problem, don't hesitate to contact me. You can always use web assign question to the instructor to let me know if you have a problem when you are doing your homework. All the best.